Good day, students. In this clip, we're going to be going over two examples on how to find limits graphically and numerically. And also, we're going to be talking about continuity in the context of these examples. All right, so let's take a look at some examples. For question one, this actually is problem number one. Let's say we are provided with this graph right here. So our task is to basically answer these questions for this graph. Okay, so this is number one. And for this number one, we're looking at x equals 3. All right, that's where the action is happening. All right, let's go ahead and answer the question. So question number one, the A part, we are asked to find the limit as x approaches 3 from the left and the right side. So we're to find the limit as x approaches 3 from the left. And then for the B part, we're gonna find, let me put function here, of the function. All right, this is the function that's under consideration. It's a piecewise defined function. And then for the B part, we're gonna look for the limit as x approaches 3 from the right of the function. Okay, so what on earth does this mean? Well, to help you gain a visual understanding of what's happening here, let me give you an illustration real quick. All right, so let's take a look at this. This is the same graph. I just graphed it in a different program. It's illustrated in a different program here. So we're asked for the limit as x approaches, this is 3 right here. As x approaches 3 from the left and also from the right. So what on earth is the limit as x approaches 3 from the right of this function? So let me show you a visualization. See what's happening here. From the left, what's happening? You notice that as the x value is getting arbitrarily close to this a value, which is 3, what is happening to the function? What value is the function approaching? So let me show you again. You see as it's getting closer and closer, what value is it approaching? Let's do that again. You can see as it's getting closer and closer to a, which is 3, the function is getting closer and closer to 3. Remember, the limit of a function is the value the function approaches as x approaches a value. All right? So from the left-hand side, we can see that as x is getting close to 3, the function itself is getting close to 3. Okay, so the limit from the left-hand side of this function is clearly 3. Okay? All right, how about the right? On the right side, what's the story there? So if we are approaching from the right, as x is getting arbitrarily close to 3 from the right, what value is the function approaching? That's what the limit is, right? So as we're getting closer and closer to 3 from the right, the function is approaching a certain y value. So let's see what that is. So you see it's getting closer and closer to a certain y value as x gets closer and closer to 3, and that y value is 4. Okay, so you see that's the right-hand limit. Okay, so let's take a look at both of them. As we get closer and closer to the same y value, to the same x value, they both approach in different y values. Okay, so for the left side, it's 3, and then for the right side, it's getting closer and closer to 4. Okay, so that's the left and the right-hand limit. Okay, so let's go back to the problem. All right, so for the problem, the limit, this is the same function we just looked at the animation of. As this function is getting closer and closer to 3 from the left, sorry, this is x3 from the left. As x is getting closer and closer to 3 from the left, the function itself is approaching 3. Okay, so the left-hand limit is 3. How about the right-hand limit? As a function, as we saw just now, as x approaches 3 from the right, we notice that the value of y of the function is getting closer and closer to what? To 4. Okay, so the right-hand limit is 4. We were also asked to find, this is for the a part, we're also asked to find evaluate the function at x. So at x equals 3, what's the value of the function? So what's happening at the point? What is f of 3? Okay, what is f of 3? So this is the point right here. F of 3 basically asks, what is the output if the input is 3? So we just simply read it. So we go from 3 to the line, and then what's the output? The output is 1. Okay, so we can clearly see here that f of 3 is 1. Okay, so that answers the A part. Now, what do all this mean in the context of limits and continuity? That's what B asks us to do. We're supposed to state our conclusion in word form and also symbolically. Okay, so let's go ahead and do that for the B part. So this is going to be our conclusion. Conclusion. All right, I'm going to make a nice little table here so we can see what's going on. Um, on the first on the first column, we're going to deal with the word representation, the verbal, and then on the right side, we'll do the symbolical representation of our conclusion. Okay, so this is a verbal. I can call it word conclusion. So we're going to make a conclusion based on two things. The first one is limits, and then the second one is continuity. Okay, so concerning limits, what does this result that we have here tell us about the limit of this function as x approaches 3? Well, since the left and right hand limits so left and right hand limits are different the limit as x approaches 3 does not exist. Okay, does not exist. So basically, if there is no statement of directionality, the assumption there is we're looking at both directions. Okay, so since the left and right hand limits are different, the limit as x approaches 3 does not exist. Okay, all right, so this is in word form. How about in symbols? If we want to convey this mathematically, well, we can just simply write since the limit as x approaches 3 up from the left of the function is not equal to the limit as x approaches 3 from the right of the function, that implies that the double-sided limit as x approaches 3 does not exist. Okay, so that's your conclusion right there. Okay, let me just put in f of x here. I need to move it a little bit to make space. So the limit as x approaches 3 of the function does not exist. Okay, because the left hand limit and the right hand limit are different. Okay, so there you have it. All right, so how about concerning continuity? What on earth does this result that we have tell us about the continuity of this function? All right, so let's go ahead and consider that. That's going to go into our next row, continuity. We can arrive at a conclusion from here. So continuity, write this down, continuity. So we know that left and right hand limits do not exist, but they both approach finite values. Okay, so since the left and right hand limits are different. So if they're both different, we know for a certainty that there's going to be a discontinuity there. But the question is what kind? If the limits are different but they're both finite, then we have a jump discontinuity. But if they're both infinite, then we have, if one or both of them are infinite, then we have an infinite discontinuity at that point, okay? But since the left and right hand limits are different and finite, okay, and finite, so that tells us that there is a jump discontinuity at x equals 3. Okay, so that's how continuity is connected here. All right, how do we depict this in symbolic form? All right, so if we want to communicate the same information symbolically, we need to make two statements. First of all, we have to state that there is some kind of discontinuity, which basically is based on the fact that the two limits are different. So first we're going to say, right, if, or say, we can say since, start off with since the limit as x approaches 3 from the left of the function is not equal to the limit as x approaches 3 from the right. Okay, this statement automatically indicates that there is going to be a discontinuity for sure. So the question is, what kind of discontinuity? Well, that depends on what they both approach. So they're both finite, right? So if they're finite, that means that they're not infinite. So how do we represent that? So since this is true and the left-hand limit is not equal to plus or minus infinity. If it's not plus or minus infinity, it must be finite, right? And plus or minus infinity is also not equal to the right-hand limit. X approaches 3 from the right. This automatically implies that they both approach finite points, hence we have a jump discontinuity. So you start from a finite point and you jump to another finite point. So this implies jump discontinuity at x equals 3. Okay? So this is how you convey the same information symbolically using the limit notation. Alright? So this basically shows a connection between limits and continuity. Alright. Alright, let's take a look at question number 2. We're going to do exactly the same problem. It's the same kind of problem, but we're going to look at the numerical representation here. Okay, so we have a table that represents a function. So we just examine this problem. For number 2, we're looking at, this is going to be for x equals 1, okay? So by inspecting this function, can we answer the following questions? Left and right-hand limits relative to x equals 1, and also state our conclusion verbally and symbolically, okay? So let's go ahead and find the parts. So to help us gain a visualization of this, it's good to make a number line, because these numbers is really hard to have a visual as to what is going on, okay? So we are looking at x equals 1, so let's say this is 1, all right? And you notice this value is 0.99. We can put it here. This is 0.9999. This point right here. And then we have another point, 0.999. And then we have another point right here, 0.99. Okay? So we can see that when we are approaching from this direction, we're going in this direction right here. So this upper portion right here is the left-hand limit. Left-hand limit, or x is approaching 1, from the left. Okay? How about downstairs here? What's going on here? If you're approaching 1 in this direction, obviously you can conclude that it's going to be from the right, right? X is approaching 1 from the right. All right, let me just put it on the number line so we can see. So this point right here is 1.00001, and this point right here is 1.0001. This point right here is 1.001, and this point right here is 1.01. So you can see that as we approach 1 from this direction, this is the right-hand limit. Okay, this is x approaching 1 from the right, and then this business right here is x approaching 1 from the left. All right, so with this visualization, hopefully we now know where our left and right-hand limits are, so we can go ahead and answer the questions, okay? All right, so let's take a look at the A part. A part, the limit as x approaches, let me write that again. The limit as x approaches 1 from the right, from the left, as x approaches 1 from the left of the function is what? So the question is, as x gets really, really close to 1, where is this function getting close to? You notice as the zeros get larger more and more, this value is getting really small, this decimal value. So eventually you're going to have so many zeros that you're going to be left with just what? which is 2. Okay, so the left-hand limit is 2. All right, how about the right-hand limit, though? The limit as x approaches 1 from the right, that's the right-hand limit of the function. Now, as we get closer and closer to 1 from the right here, what do we notice? You're getting more and more 9s, right? So if you have infinite number of 9s, it's going to basically become 2, okay? Because you have so many 9s that is basically the same thing as 2. So this is also equal to 2, all right? And then lastly, we're to evaluate the function at the point x equals 1. So lastly, what is f of 1? F of 1 is 7. Okay? All right, so now that we have the information, let's see if we can draw a conclusion using this information. Okay? So part B, we're going to make our conclusion or state our conclusion. We're going to do it in two ways. We're going to do this verbally in word form or word or verbal form, and then we'll do it symbolically. Okay, all right, so let's make our two columns. In the first column we're gonna do word in word or verbal form, and then in our second column we're gonna do symbolic form. Okay, so that we see the connection here. Okay, so now let's see. We're going to talk about our conclusion in two areas. First of all, what does this tell us about the limit? Okay, so limit to conclusion. Since the left and the right hand limits, so the left and right hand limits are equal or the same, are equal, what does that tell us? That tells us that the limit as x approaches 3, as x approaches 1 exists. Okay, and what on earth is it? Is the value that they both equal to, which is 2. Okay, all right, let's write out in symbolic form, or let's also include here and is equal to 2, equal to 2. In symbolic form, we're going to say the limit as x approaches 1 from the left, so the left-hand limit is equal of the function, is equal to the right-hand limit. So since this is true, of the function this implies that the limit, the double-sided limit, as x approaches 1 of the function exists. What on earth is it? It is equal to 2. Okay? So remember that in order for a limit to exist, the left and the right-hand limits must be the same. All right? And that the limit value is basically what they are equal to. Okay, so now how about continuity though? What conclusion can we state here concerning continuity using the results that we just got from the problem? All right, let's go ahead and take a look at it. So continuity. All right. Now so I will say here that since the left and the right hand limits are equal but not equal to. Now, if they're both equal, we automatically know that jump and infinite discontinuity are out the door. Okay? So if the left and right hand limits are equal, but are not equal to the value of the function, we have a problem. And the problem is a break where at the point, because the value of the function is a point. Okay? So since they're equal but not equal to the value of the function, we have a point or removable discontinuity. Okay, so that's what we have here. Since the left and right hand limits exist, it's either going to be it's continuous or a removable discontinuity. But since the value of the function is not equal to the limit, that means we have a hole right where they're approaching. So we have a point or a removable discontinuity. Okay. All right. So how do we write that in symbolic form? We can write. Oh yeah, I was supposed to put a since here. Um, since the left-hand limit, x approaches 1 from the left of the function, is equal to the right-hand limit, that automatically means that we do not have any jump or infinite discontinuity. It's either going to be continuous or the point discontinuity. But since these two limits are not equal to the value of the function at that point, f of 1, okay, is not equal to f of 1, this implies that we have a point or removable discontinuity at x equals 1. All right, removable discontinuity at x equals 1. Okay, so this is basically what this result is telling us. This is the conclusion that we can draw. All right, so there you. All right, so how well did you get the example I just showed you, or the examples I just showed you? Well, I want you to try this. Try this example, okay? So considering this function on the right here, this is question number 3. I want you to find the left and right hand limits and evaluate the function at x equals. In this case, we're going to look at x equals 2. All right, so everything is happening around x equals 2. Find the left and the right hand limits, and then evaluate the function at x equals 2. And then I want you to state the conclusion for me. State it verbally and symbolically, okay? In the comment section below, you can write down, type in the verbal conclusion, and also the answer for your left and the right hand limits, okay? Or if you have any misunderstandings, you can post it in the comment section to let me know what you think. Thanks so much for taking the time to watch this presentation. You can feel free to subscribe to my channel by clicking here. Also, don't forget to post your answers in the comment section. More clips can be found on microsoft.com/calculus, or you can just scan this QR code for direct access to a collection of cool tutorials such as this. Thanks again for watching. Have a wonderful day.